Welcome to Electronic Seed YouTube channel. Today in this video, we will learn about Boolean algebra, laws, simplification, and alternatives. Let's get started. Boolean algebra forms the very foundation of how we design digital logic circuits. I've noticed many students struggle once we move past simple truth tables and basic gates. Having redundant logic in your design can increase power consumption, chip area, and signal delays. That's why systematic minimization is absolutely essential for building efficient digital systems. In this article, we'll cover the core Boolean rules, their applications, and also their limitations. You'll learn how to simplify expressions and understand that minimal forms aren't always unique. Finally, we'll see when it's time to switch to Carnot maps for larger systems. This slide shows the table of contents, outlining all the topics we will cover. Boolean algebra gives us algebraic rules for binary variables, which can represent true or false, or 1 and 0. The basic operations are and written as a dot, or written as a plus, and not written as a prime symbol. Our main goal is to reduce the gate count, which leads to lower cost, less power, and shorter delays. For example, consider an air conditioner controller with the expression y equals t and h, or m and not a. We can reduce this expression using Boolean laws, as we'll see later. Every Boolean manipulation comes from just a small set of fundamental axioms. If you memorize these laws, you'll be able to simplify expressions very quickly. The complement or not operation simply flips a variable. 0 prime gives 1 and 1 prime gives 0. Double complement means that complementing a variable twice brings you back to the original value. For instance, an active low signal that gets complemented twice returns to its original state. We use this rule to remove redundant inverters from a circuit. This table shows the AND operator laws, including idempotent, identity, and domination, with expressions and explanations. This table summarizes the OR operator laws, idempotent, identity, and domination, showing how OR behaves with itself, 0, and 1. The domination law, where any variable OR'd with 1 equals 1, can often eliminate entire subexpressions in your circuit. Our unlock signal F is defined as a prime B plus BC plus ABC. A represents whether the keycard has been inserted, with 1 meaning yes. B indicates whether the correct pin has been entered. C tells us if the override switch is active. This expression uses 3 AND terms combined with a single OR operation. First, we can factor out B from the first and third terms. This gives us B times the quantity a prime plus a C. Now apply the absorption law, which says a prime plus a C simplifies to a prime plus C. We can verify this by checking both cases. If it is 1, then 0 plus C equals C. If it is 0, then 1 plus 0 equals 1. So B times the quantity a prime plus C becomes a prime B plus BC. Our simplified minimal expression is F min equals a prime B plus BC. The original circuit needed two 2-input AND gates, one 3-input AND, and one 3-input OR, for a total of 4 gates. The simplified version uses just two 2-input AND gates and one 2-input OR gate, so only 3 gates. By eliminating one gate, we achieve lower power consumption and shorter propagation delay. One drawback is that minimal forms aren't unique. Different engineers might end up with different-looking expressions. It becomes very tedious when you have more than 3 variables due to combinatorial growth, and it's easy to make mistakes. Boolean algebra has no built-in way to handle don't care conditions. In practice, it's often limited to 3 or fewer inputs. For larger systems, we need graphical methods like Carnot maps. A Carnot map is a visual rearrangement of the truth table that makes minimization more intuitive. You group adjacent ones together to extract the simplest sum of products expression. Carnot maps can handle 4 to 6 variables and naturally incorporate don't care states. Let's apply the K-map method to our lock system expression F equals a prime B plus BC plus ABC. First, plot the truth table values onto a 3-variable Carnot map. The adjacent ones form 2 groups, which correspond to the terms a prime B and BC. This yields the same minimal expression we found earlier, but without any algebraic manipulation. I recommend using Carnot maps whenever Boolean algebra becomes too unwieldy. Boolean algebra remains essential for truly understanding how logic circuits work. It's best suited for small-scale simplifications and for educational purposes. The laws of Boolean algebra form the foundation for Carnot maps and even electronic design automation tools. Engineers who master Boolean algebra are much better at debugging handcrafted logic. For designs with more than 3 variables, switch to Carnot maps or automated minimizers.